Hi everyone, today we're going to talk about acid and base properties of salts. This is tied to learning objective from the College Board that students can identify a given solution as being a solution of a monoprotic acid or base, including salt, and calculate the pH and concentration and infer the relative strength of the weak acid or base from the given equilibrium concentrations. Basically, we're trying to take a salt solution and identify whether it's neutral, acidic, or basic. First, neutral salt solutions. They are made of cations of strong bases, such as sodium ion, potassium ion, of like sodium NaOH and KOH. Then they have anions from the strong acids, such as the chloride ion and nitrate ion, because they have no affinity for the hydrogen ion. So when a salt is made up of these cations and anions, they have no effect on H+ when dissolved in water, and the pH is neutral. Now let's take a look at the basic salt solution. They have anions that are made of conjugate base of weak acids, such as the fluoride ion, the nitrite ion, the acetate ion, etc. When they ionize in water, they form hydroxide ion, making the solution basic. So the F- have a great affinity for the hydrogen ion, as illustrated in the above reaction, F- with water to form HF and OH-, and then the salt solution is then basic. Regarding acidic salt solution, there are two sets of rules. Rule number 1. If the cation is made of the conjugate acid of a weak base, such as the ammonium ion, the C2H5NH3+ ion, and the CH3NH3+ ion, they ionize in water to form the hydronium ion, making the solution acidic. The second set of rules govern these transition metal ions, which are small but highly charged. They form hydrated ion in water, and from that, the hydrogen ion can be donated to make the solution acidic. For example, aluminum ion 3+ will hydrate with 6 molecules of water. Now then we take 1 water molecule from the hydrated ion and dissociate it to donate the proton, and therefore we now have left Al, H2O5, OH, overall 2+ charge, and such solution is acidic. Now let's try to practice with a few salts and see if we can identify or predict their acidity or alkalinity or neutrality. Take the first group, sodium chloride, potassium bromide, and calcium nitrate. Notice that the Na, the K, and Ca, they are all the cation of strong base, where the chloride, bromide, and nitrate ions are the anions from a strong acid. Therefore, the pH is neutral. They do not contribute to pH in the solution. The second group has NaF, calcium acetate, and potassium nitrate. Again, with Na, calcium, and potassium ion, these are the cation of strong base. They don't contribute to pH. However, with the fluoride, acetate, and nitrite ion, these are the from the weak acid. So they will ionize in water to form this hydroxide ion. Therefore, a basic solution is formed. The last group, iron 3 chloride, aluminum nitrate, and ammonium bromide. Again, we don't need to pay any attention to the chloride, nitrate, or bromide ions. They do not contribute to pH. However, with the Fe3+, Al3+, and ammonium +1 ion, they contribute and donate a proton when they are dissolved in water. Therefore, the solution is acidic. Try practice problem number 2. The solution of ammonium nitrate, is it acidic, neutral, or basic? Now, here we dissociate it into the ammonium ion, take the cation, and then look at it one at a time. It is a conjugate acid of a weak base ammonia. So in water, it will ionize and form the hydronium ion, and therefore we need to go back and check out the Ka value, which is 5.6 times 10 to the minus 10. Then we look at the anion, the nitrite NO2- ion, which is a conjugate base of a weak acid. So when it ionizes in water, it forms the hydroxide ion. That means we now need to calculate the Kb value, which is 2.5 times 10 to the minus 11. When you compare the Kb with the Ka, we notice that Ka is greater, therefore the solution is acidic. Let's try practice problem number 3. For the solution of Na2HPO4, is it acidic, neutral, or basic? Now here we disregard the Na plus, which is a spectator ion, and pH is neutral. Let's focus on the HPO4 2- ion, which is amphoteric, meaning it can act as an acid and a base. When it's acting as an acid in water, it would donate the proton to form the hydronium ion and the phosphate 3- ion. Therefore, we need to go and check out the Ka value. But are you going to take Ka1, Ka2, or Ka3? Well, this is the transfer of the third proton. Therefore, we go to use the Ka3 value, 4.8 times 10 to the minus 13. When it's acting as a base, it will then ionize with water and forming the hydroxide ion and the H2PO4- ion. Now the formation of the hydroxide ion means that we need to go back to check out the Kb value, which is calculated by Kw divided by Ka2. And why Ka2? Because we're talking about the transfer of the second proton. So it's calculated as 1.6 times 10 to the minus 7. And obviously the Kb is greater than Ka, so the overall solution is basic. Whenever you have such polyatomic ions ionizing in water and with the proton present, we have to go through these kind of calculations. But make sure that you do not pick the wrong Ka value in your calculation. Look for which proton is being ionized. Practice problem number 4. Solution made by adding sodium hypochlorite NaClO to enough water to make 2 liters with a pH of 10.5. Let's calculate the number of moles of NaClO, the sodium hypochlorite, that were added to water. So from the pH, we gather the pOH is 14 minus 10.5, which is 3.50. Now then we take the anti-log of 3.50, then we have 3.2 times 10 to the negative 4 molar. Now, when we write the equation of the hypochlorite ion in water forming the hypochlorous acid and hydroxide ion, then we need to calculate Kb because the formation of hydroxide ion dictates the use of Kb, which is Kw over Ka. And this is equal to 2.9 times 10 to the minus 7. Now, the Kb expression is written as HClO times OH minus over ClO minus. Therefore, we can now use the Kb value and substitute in the hydroxide ion concentration over the original ClO minus. Notice that I take the square of 3.2 times 10 to the minus 4 because the HClO and the hydroxide ion concentrations are equal. Now, this ClO minus ions concentration is solved as 3.5 times 10 to the minus 1 molar. And because we have 2 liter solution, it turns out to be 0.70 mole of NaClO, sodium hypochlorite. To summarize what we have learned today, we have learned to follow a set of rules to classify the solution, the salt solution, as acidic, basic, or neutral. And that pH depends on specific cations and anions involved in making the salt. Secondly, we learned how to calculate the moles of salt needed to prepare a solution of a given pH. I hope that you find this video helpful to you. From the team of MLCA, we'd like to thank you for watching our video and look forward to seeing you again soon.